This video will walk through the solutions to 4 applications of logarithms. Here are the 4 examples, and you can see here at the top of the screen in yellow the formula that we use for exponential growth and decay. Now in this formula, A is an amount. So for example, for number 20, the amount has to do with population. A sub 0, often read A naught, is going to be the initial amount. So at the start of whatever year we are in, the amount, and in this case, the initial amount is for number 20 is 470.5, and that's representing million, so 470.5 million. And then we have our constant E to the exponent of k times t. Now t is the number of years, time, and k is the decay or growth constant. And in a physics or chemistry class, you might find k through some experiments. But in our math examples, the k, the constant of growth or decay, is going to be given to us. Now, when we read number 20, all you need to do for this example is to be able to understand what it's asking, because the answer is actually already given to us in the equation that we're given. The exponential model, A, amount, equals 470.5. E to the 0.03t describes a population, A, of a country in millions. And this is t years after 2003. So we see that t is equal to the years after 2003. So in this question, use the model to determine the population in 2003. All it's asking us for is A naught, the initial amount, the initial population, and that would be 470.5 million. And that's all we have to do. Now, if we did see that t is equal to 0, and you substituted t with 0, we'd have e to the 0, which is 1. So all of this would just change to 1, and there we'd have our 470.5. But you don't have to go through that process if you simply recognize how to read the equation. Let's look at number 2. For this second problem, number 21, we're given the equation or the formula. The amount of population is 324.7 e to the 0.011t when t is the number of years after 2003. And our problem is asking us to find the time, find the year, when the amount is 351. So what we're going to need to do is find t, the number of years after 2003, and then determine what year that will be. So I have replaced the amount with the 351 that they gave us, and we're looking for t. To solve this, I'm simply going to use what I know about solving an exponential equation, and it's going to involve having t, the variable, is an exponent, so I know that I'm going to need to take the log of some base of both sides. Now, since I have an e in the problem, I might as well use the natural log base e. Before I do the log of both sides, it's going to be a little easier, more simplified, if I isolate that exponential term first. So I'm going to isolate this e to its exponent by dividing both sides by 324.7. Now I'm not going to actually divide that yet because I don't want to end up having approximation in my calculation. So I'm going to keep it 351 divided by 324.7, which is fine. And that's going to equal e to the 0.011. Don't lose that second 1 in that k. K in this problem equals 11 thousandths, 0.011. So what I'll do now is I'll take the natural log of both sides because I want to get this t down, right? So when I take the natural log of both sides, that exponent, the 0.011t, just falls right down in front. So now I could see that the natural log of e is 1, and if I divide both sides by 0.011, I'll have t. So t is equivalent to the natural log of 351 divided by 324.7, all divided by 0.011. Let's look at how to calculate this. On my calculator, I'm going to type in ln. This first parenthesis opens up automatically. I'll do 351 divided by 324.7 and then close the parenthesis. And then I'm going to divide that by 0.011 to get this divided by 0.011. And when I did that on my calculator, I got an approximation of 7.08. So we could say that that's approximately 7 years. 7 years after 2003 is going to put us in the year 2010. So I could say, therefore, the population reaches this amount in approximately the year 2010. When I move on to number 22, I see another problem using the same model. An artifact had 16 grams of carbon-14 present, and originally had 16 grams of carbon-14 present. In the K model, A equals 16e to the negative 0.000121 times t describes the amount of carbon-14 present after t years. So we can use this model to predict how many grams of carbon-14 should be present in 6,540 years. So in other words, to interpret this, we want to find the amount of carbon-14 when t time equals 6,540. So really all this is a calculator problem. I'm going to put this into my calculator. This is precisely what I'll put in. I'll put 16, and then I'll find the e to the x button. It's the second to the ln, to the natural log. So 16 second ln, so that gives me 16e to the x. And then I'm going to put in the parenthesis, the first parenthesis, negative 0.00121, close the parenthesis, or you could say times. Actually, don't put the closed parenthesis, I'm sorry. Just put times when you do this. So let me write that here so you can see that. Times 6,540, and then close a parenthesis. Now, if I close a parenthesis after that first one and then do times, it's actually going to multiply the whole amount, this amount that's already exponented. It's already raised to the exponent. It's going to multiply that by the 6,540 rather than making the 6,540 part of the exponent. So again, let me say what you put in the calculator. 16, and then e to the x, and then when we type in the exponent, we're going to put negative 0.000121 times 6,540, and then close the parenthesis, equals. Now when I did that, I got 7.25, and so in approximately how many years will that be? We could say, therefore, the amount present will be 7 grams will be present in 6,540 years. Let's look at number 23. Now, this example is going to require us to do a little bit more interpretation. What we have is a prehistoric cave painting, and historians used to use carbon-14, the amount of carbon-14 in a product, to determine its age. So if the paint contained 14% of the original carbon-14, then use this decay model for carbon-14. So in other words, this negative 0.000121 is the K for carbon-14. That describes how quickly carbon-14 decays. use this exponential decay model to estimate the age of the painting. Well, if we're given that the amount of carbon-14 now, A, is 14% of the initial amount, A naught, then what we can do is we can reduce this down to a different equation. When I replace A with 14% of A naught, then I can see that the A naught is going to divide out of both sides. So now I've got 0.14, 1400ths equals E to this exponent. To get the T down from that exponent, I'm going to take the natural log of both sides. And when I take the natural log of both sides, this exponent falls down in front. So I would be able to then solve for T. Now the natural log of E is just 1, so it goes away. And I've got the natural log of 1400ths is going to be equivalent to the exponent negative 0.000121 times T. So to solve for T, I'll simply divide both sides by negative 0.000121. And that'll give me T. So there's the exact amount for T. We also need to estimate that, well, not estimate, but get an approximation for T. And when I put that into my calculator, I get that T is approximately 16248.86658. It's usually going to suffice to round to 4 decimal places. So I can see that that would be, the 5 would cause this to go up. So we'd get approximately, or actually this is in years, so we could round this one to the nearest year. So this would be in about 16,249 years. So therefore, the estimated age of the painting is 16,249 years. Well, I hope that this explanation through these 4 different application problems helps you. If you do need help with further help with any of these, please reach out to me or to a tutor.